this topic. There's a lot of AI forums that happen throughout the year, and a lot of them have moved to these remote sessions. And what I see as a general trend is a focus, a historical focus on what these sort of small scale models and proofs of concept can do when the AI engineer owns and fully controls the data and can configure the system to be optimal for the AI implementation. What we found in real world, large scale, high risk settings is that those laboratory conditions that yield really interesting demonstrations oftentimes aren't available for these real world settings. So what I'd like to share with you today are some of the lessons that I and my colleagues have learned. It's always an AI, like any good engineering effort, is a team sport. So please don't take all of these as sort of my personal, only insights. Many of your colleagues may have had similar observations as well. And because I've been blessed with an opportunity for the last, say, 8 to 10 years to lead a handful of human-centered technology efforts, and most recently attempting to lead in the U.S. Efforts to focus on trustworthiness, assurance, and human-centered artificial intelligence engineering. As Carmen mentioned, I'm currently working as a research professor at Virginia Tech. I have an extensive military operations background, but also have had a significant opportunity to lead technology development efforts from the government sponsor role. And as I'm leaving the military, also took the opportunity to stand up a company called the Bulls Run Group, which is attempting to do what I'm doing for Virginia Tech in an academic capacity, also in a commercial capacity. So there's a lot of different ways that you can reach out and touch me with me and follow up on any of these observations. So this is a couple things that I'll share with you, just some observations from industry that you may have yourself made about AI recently. Some lessons that I took away from the stand-up of the first 6 artificial intelligence missions that we were portfolios, as we were calling our missions, our portfolios missions in the Joint AI Center for the U.S. Defense Department. And then to talk to you a little bit about what we're doing at Virginia, in the state of Virginia, to stand up an AI assurance test bed to kind of close the gap. So many of you are familiar with this. Some of you are currently living in Germany, where the German government has, in the past, cautioned against and prohibited the company Tesla from declaring its automated systems, driving support systems, as we'll call them, quote unquote, autopilots. This is important because this is Germany in this case was one of the first governments to push back on misleading labels for AI implementations. The Tesla Auto Company, since they started deploying these automated driver-assisted cars, have had a number of fatal crashes, 13 since 2016, and the Tesla Corporation will declare that this is actually a really low crash rate in comparison to other vehicles. But when you compare it to another strategic disaster for a large motor company, the Ford Motor Company, back in the 70s, they deployed a Ford Pinto to compete with Japanese the auto industry for small cars. Only 27 deaths over a 5 to 6 year period resulted in significant strategic deficiencies for that company. And you'll note that the Tesla vehicle is sort of on track for that. And why is that? Because what you saw, I have as a picture on this slide, is a display of the A panel, the panel that's directly in front of the driver while the vehicle is in operation. And what the autopilot system does, this driver assist system does, is it assumes that you're going to maintain contact with the steering wheel and you're going to maintain active driving awareness over this vehicle while it is performing the normal control features, control operations for that vehicle. So in reality, what this driver assist system is doing is it's transferring what is normally an active direct control task from the driver, changing that task into a vigilance monitoring task, which is in fact actually much more cognitively difficult. And you're leaving by putting a label on the system as autopilot, it conveys to the driver misconceptions about the ability of that control system to navigate the vehicle safely in all conditions. And so this is one of the first observations that we're making about in this case, the auto industry and its deployment of autonomous systems, is that labels are really important. When the driver assumes that the artificial intelligence is able to fully navigate the vehicle, they turn over an inappropriate amount of trust to that system, and they misuse it, and that's what's happening here. Another lesson from the air industry, the aviation industry, commercial aviation in this case, is the Boeing 737 MAX. In this case, the Boeing Corporation was in very close competition with Airbus to deliver a new version of its long-haul aircraft, the 737. Very successful, very safe airframe. So they had three corporate goals: good, fast, and cheap. And most engineers that have delivered products into the real world understand you can't ever achieve all three of those in the same system. But they had an idea of delivering a new airframe that would require no new training. This is important because if the airframe required new training, it would be deemed it would slow its ability to be approved by the FAA. Airbus was in competition to it, so it needed to get it out fast. And this system would be cheap for customers because it would leverage new technology, new turbine engine technology that would reduce fuel consumption. So at the strategic corporate level, there was, again, just like Tesla, strategic messaging about what this system ought to do and how it ought to operate that pushed against the better judgment of subordinate engineers. The problem here is illustrated on the left-hand side of this slide. When you introduce this new turbine to the wing of the 737, it changes the aerodynamics of the aircraft. It's a larger engine, and it's more powerful. It's a more powerful engine, and so you have to, in order for this aircraft to use, in order for you to mount this engine on this the wings, you have to move it forward and up on the location of the wings. What this does is tends to change all of the aerodynamics, and so this would require training of a new pilot because you're in fact actually flying a different aircraft. The solution was to mask these features from the pilot by introducing an automated data processing and control system, the MCAS, give it an innocuous name, maneuvering characteristics augmentation system, and then don't even train any of the pilots on it. Don't even tell them that it's there. Hide it in the literature in the back and the appendices of the operating manual in case anybody ever asks about it. But this system would do is it would sense the angle of attack, the orientation of the aircraft while in flight, because when you applied power to this engine, the nose would tend to pitch up, and whenever an aircraft pitches up too steeply, it tends to go into a stall condition, and so this stall condition would be prohibited by this automated system that would sense when the nose was rising and then automatically correct the trim on the wings so that without involving the pilot. This is all works. This is all in an ideal laboratory setting. Great. The pilot never needs to worry about it. Unfortunately, this is causes repeats of some of the earlier autopilot system failures of the 80s, in which the aircraft would be making adjustments while in flight that were hidden or masked to the pilot, and then immediately turn over once it had exhausted its ability to cope with the current situation, turn things over to the pilot, and these aircraft would fall out of the sky because the pilot was unaware of what had been done by the system leading up to the point of failure. In this case, we had a number of fatal incidents, all sort of unfolding in a similar way, where the pilots in the aircraft would be struggling over a series of minutes with this MCAS system, not knowing that they could even deactivate it because they didn't know it was even in the aircraft. Again, while this is meant to be a pilot aiding system, by hiding it and giving insufficient feedback, not allowing the human to remain the source of resilience and the agent for goal setting in the system, they designed in fatal flaws. So these things are important for us as we think about how we're going to deploy AI in increasingly high-risk settings. This is there's a much larger consequence for military settings, for aviation settings, or even personal automotive settings than there are with training a search algorithm on Netflix or Google, where the consequences for failure might be a couple lost minutes and the confusion about what the search results yielded. These complex systems beg the first order question of most users, which is, what is my system doing? And so when we introduce as engineers or salesmen terms like the computer is learning, the system is perceiving, it is predicting or paying attention, and in fact that's not what the mathematics are doing. I don't think of my daughter going to a third grade class, even though when it's even in remote conditions here, as tuning coefficients. She's learning generalizable skills that she can reapply into other settings. And so when we put a label like the computer is learning, the everyday user interprets that in the ways in which we use those terms in common everyday settings. The computer is not perceiving, it's merely classifying sensory data. When you talk to a mathematician, some of you may be mathematicians, mathematicians talk about predictions as determining the likelihood that a value or a state exists in a data set. That's not what everyday people think of as predicting the future. Many people would think of that as predicting the past. It's actually a state that already exists, and you're just determining whether or not it exists in a data set. So the real point here is that we need to find accurate labels for the computational methods that these systems are using. That in fact we should never be seeking to substitute humans. What we should acknowledge by the history of technology inventions and reinventions and reapplications is that technology never replaces humans. It changes the roles, the responsibilities, and the skills that are needed by humans to ensure that systems can operate safely, effectively in changing real-world conditions. And so good systems, even especially AI systems, the more complex the system, the more important it is for us to tend to things like supervisory control. Where and how are my users, or my humans that are going to be responsible for the success or failure of these systems, where are they getting the right feedback? And these are questions that many of our AI evangelists are not tending to right now. So the gospel that I've been preaching, from the Defense Department and now in industry and academia, is that let's make sure that we're keeping humans as the source of resilience. We've learned a lot of lessons in the stand-up of the Joint AI Center. The Joint Artificial Intelligence Center is the Defense Department's transformation agent. It has a mission of transforming the Defense Department with and for the use of artificial intelligence. This is important because this suggests that what we're about is not just small-scale research demonstrations. We're about delivering useful capabilities to warfighters and those who support warfighters in real-world settings. And so what we did in the AI Center is we stood up in the first year, and we are still continuing to operate these as I'm leaving the organization, 6 missions that are essentially portfolios of AI product lines or technology development efforts. And because we wanted to expose the breadth of problems that exist across this world's largest bureaucracy. Are the problems generalizable? Do they apply? Does a cyber AI problem apply to predictive maintenance? Does it apply to a healthcare setting? And the answer is yes. These are generalizable lessons that we found in that I'm highlighting here in individual missions, but we found different instantiations of these problems, these challenges, or barriers to enterprise scale AI adoption, delivery and adoption that we need to understand as we invest millions or if not billions of dollars in these new technologies. That problems, and I'll just highlight a couple of these, and I'll leave them I'll return to this if we have other questions. But some of the points here that you find is that when you're delivering systems to militaries or companies that have that are very mature and have existing systems, that these legacy systems and their methods of acquiring new technologies impact or constrain technology innovations. And you have to understand how those legacy systems, whether it's an artillery system or a military, command and control system, or maybe it's an aircraft or an air traffic control system, all of these systems, the introduction of an AI implementation is never going to be justification for a greenfield approach to design. In the U.S. military, we have over $1.5 trillion in just what we call our major ACAT-1, our biggest military systems. Probably over 2 to 3 trillion in all of our military investments. So just because someone has a new idea about how to process data, that might be collectible in those systems, isn't going to cause us to jettison all of that investment. So we need to understand how we integrate in these technologies. Some AI implementations may require data that just is not being collected today. And if it is being collected, it's not being curated or stored or is not shareable in the ways that AI implementation might need. And that's what we're finding in cyber settings where individual network defenders, small groups that are responsible for portions of the defense network haven't been incentivized to collect, curate, share, and store data that will allow us to make enterprise scale insights. There's been a lot of commercial interest in delivering robotic process automation, basically just fairly basic bots that would automate, maybe data collection, parsing of data, accessing databases or populating databases. These are sort of really basic rudimentary operations that you can automate and save lots of time. Well, in the Defense Department, like many other mature large bureaucracies, we have policies that limit the ability to deploy those bots. We protect our databases with multi-factor authentication, and so we're not going to give 2 forms of authentication to a piece of software script. And so these policy barriers, whether they're a limitation on keeping experts working on in key work domains, or policies limiting the ability for certain groups to share data with others, have great impacts on your ability to deploy things at enterprise scale. One of the things that we ran into with healthcare, because you would think healthcare is a really easy thing to pull things from industry into the military healthcare system. The US military has the world's largest electronic database of healthcare records. And so one would assume that if you have demonstrated some successes in a commercial HMO, a healthcare management organization, some commercial civilian hospital, about how to analyze healthcare records, that you could just immediately deploy that to the Defense Department's healthcare records and yield tremendous results. Well, in the military, in our military, we have Army, Navy, and Air Force departments that all train and incentivize their doctors in different ways. None of those doctors are incentivized to use medical coding in standardized ways because they're not reimbursed by healthcare insurance the way civilian healthcare providers are. This may be an impact, maybe a similar impact in highly socialized medicine settings that you may have in Europe. But the result is that doctors aren't collecting, they're not documenting in labeled ways the data that is necessary to deploy these large-scale analytics. And so we're finding that the data engineering efforts associated with any of these mission areas are really the big heavy lift right up front. And where are the technologies to help those kinds of data engineering efforts? Where's the workforce development to help improve the skills of the practitioners that understand what the data means, so that they can collect and curate that data for the AI engineers that are deploying models. This is a big gap for major organizations. So as I've highlighted already through some of our lessons, we have a number of non-technology as well as technology barriers to AI adoption. And if you're not willing to tackle these very difficult and many times unsexy and multi-year challenges, consensus building challenges, education challenges, then your deployments of AI will always be unsatisfactory. So one of the tactics that we started to take in the U.S. Defense Department was an attempt to decouple what we call the military technology stack. And the way we acquire systems, we have acquired systems in the U.S. military, and this is the way that a lot of people acquire them even in commercial spaces, is full stacks. I'm going to buy the sensors with the control system, with the hardware, the data transport, et cetera, all the way to the user interface for that. And that's going to be an isolated deliverable that is trainable and sustainable in the real world. The problem is that my control systems may mature at a different pace than my hardware. It may evolve at a different pace than my applications, or my user interface may actually need to be redesigned for particular missions. And so the notion here is, if we can realize a different way of contracting and engineering these elements of the technology stack, we can introduce replaceable components. And so if I'm going to deploy a quadcopter one day, I can I can continue to leverage the AI models that I developed over the last couple of years whenever I deploy the tricopter next year, some new version of that should bear no impact on the AI itself. And I'm also able to create marketplaces for many different companies or university researchers to experiment with new AI models and introducing new algorithms that could be deployed without having to replace the entire technology stack. This is a really important effort, and we think that this is probably going to be a multi-year, if not multi-decade attempt because this requires us to rethink our acquisition processes entirely. One of the last things that we did, during the first year, during this first year at the startup of the Joint AI Center, is we wanted to issue some guidance about artificial intelligence. So you may find, if you Google Defense Department AI principles, a document that describes these. And what I'll just point out in this forum is they really represent no differences to what systems engineers have documented for decades as just the principles of good resilient systems engineering. Good systems need to be observable, directable, explainable, predictable, useful. If they're not these, if you're not striving for these characteristics in AI implementations, your users are going to be surprised and your systems are going to be unhelpful. So how do you determine whether or not any of these characteristics exist for systems that are coming out of research labs and prototyping settings? Well, in the state of Virginia, we've stood up what we call the Commonwealth Cyber Initiative, and this is a state-funded ecosystem of all of the state universities, in which the mission here is to increase research and commercialization of cybersecurity technologies. One of the in Virginia Tech, the university I work at, is funded to be the hub of these universities. The idea here is that we had at this Commonwealth Cyber Initiative was that there's been increasing scrutiny on what it means to call something assurable or assured. What does it mean to say that something is trustworthy or not? And the answer is that AI assurance, like trustworthiness, is context sensitive and it's multidimensional. And so we, in the CCI, we wanted to stand up an AI assurance test bed that afforded insights into this context-sensitive, multidimensional question. What we know is that AI is no different than any other, mathematical application in a piece of software. It is a technology element that is one construct that must be considered when you think of the context in which work is done. So we know that data owners, that whether they're scientists or engineers, oftentimes don't understand data management or artificial intelligence. We know that the experts in AI engineering oftentimes don't understand work domain experiences, and they oftentimes don't have access to real world data. But the fact is that these, especially in high-risk domains, we need highly reliable technologies, and so we need a way to bridge this gap between our people that own data and problems and the people that have these insights on how to engineer artificial intelligence models. What these increasingly complex systems are prone to is even more sources of failure. There's some really nice literature recently published that talks about the risks associated with increasingly complex software, and AI is some of the most complex software. And so where you had in the past a traditional array of typical vulnerabilities in good software development, now you're compounding that with increasingly difficult to understand mathematics. So we found, and we're trying to understand how data, AI models, system architecture, and human factors influence your ability to say whether or not something is trustworthy, whether or not something is assurable. And so we're standing up this AI assurance test bed with the mission to serve as really a marketplace or a commons. I think of it as a commons, like the old village commons, where people that don't really know what a vegetable is can come and look at a vegetable and figure out, does this look like something I would like? And so the idea here is this ecosystem of researchers, students, and technologies can interact in a way that enables innovation, that allows for independence in the inspection of commercial and government AI solutions. What we see as this sort of array of use cases that this AI test bed is being stood up to comprehend with is while cyber is at the heart of it, because we're the Commonwealth Cyber Initiative, we see that there's touch points in a lot of in most areas between so we've identified an array of technology lines and research efforts across the Virginia University systems that could benefit from this test bed. And so our unique value proposition here is because you may have heard of other test beds that might be in academia or the government or even in nonprofit organizations. Our value proposition is this broad user base. It's not just one university; it's 17. It's not just one professor's lab. It's over 500 inter or transdisciplinary students and faculty members that are moving to this test bed. It's access to labeled data sets that can be shared across these projects. And it's a level of independence that doesn't necessarily have isn't there to advocate for any one particular vendor or solution. So this is what I hope that I've shared with you is just a small introduction to the big problems that you may, or many of you may already be aware of. I might have been preaching the gospel to the choir here for the last handful of minutes. But I want to make sure that we're continuing to push this message about the complexity of real-world technology deployment. AI is inherently computer and data science, but good AI is not only computer and data science. It requires interdisciplinary engineers. It requires access and buy-in from data owners and operational problem owners. And if you're not willing to roll up your sleeves and work in those settings, it's unfortunate, but you'll be delivering some disappointing outcomes.